Okay, students, I want to just introduce you to PhET interactive simulations. They're put out by the University of Colorado in America. And they're quite helpful to help you understand a few things. Today, though, I'm wanting you to look at a molecule polarity one. So we've got the HTML version here, or a shockwave flash, that'll run in your into your Chrome, for example. But when we look at real molecules, you'll see that that's not available. I've put the Java edition, which you can use there as well. So we'll have a look first of all at this one and what we're talking about, and then we'll have a look at the other one. So if we have a look here, we've got two atoms, atom A and atom B. Now, these two atoms have the same electronegativity. So remember, electronegativity is the tendency of one atom, or the ability of one atom to attract electrons over another. So if I consider the electric field, the molecule is not going to change direction or not going to align itself with any particular plate. So if I put that one there and put that one there, nothing happening. But let's see if this happens. If I turn it around the other way, it swaps around. Okay, and we'll just have a look at the partial charges and see what that's happening. So that's the positive end, that's the negative end. So this is the end producing electrons. It's going to be attracted to the positive plate. Now, this is more of an ionic sort of molecule because there's such a great electronegativity difference. We'll talk about that soon. Oh yeah, there we've got it there. So we have a look there. That's more like a polar covalent bond, for example. And if we have a look here, this is more like a non-polar covalent bond. If we have a look at electrostatic potential, we're just having a look at the negative and positive ends of the molecule. So we have a look here. The red's just indicating, well, that's a lot more electrons in this area of the molecule. So we've got a partial negative charge. So remember, it's not a fully negative one. It's just the electrons are heading to this end of the molecule. So let's go to three atoms. So water is a great example. So water is what? H2O. And water in the middle has oxygen. So it's got a higher electronegativity. And that means we've got an electric field that lines that up like that. Let's have a look at a bond dipole. So this is the hydrogen end, this is the hydrogen end, and this is the oxygen end. And you can see the molecular dipole. Well, this is the negative end of the molecule. Sorry, this one is here, B, and the hydrogens are the positive end. Now, real molecules are not available, so I've just gone into the Java edition and downloaded that, and I want to run through a few of these with you. So let's have a look at hydrogen. So remember our rule for hydrogen. It's an element. It's a diatomic molecule, and so we've just got an even distribution of electrons because same atom, same electronegativity. Same with nitrogen. So there's no difference between the electronegativity. Same with oxygen. Same with fluorine, even though fluorine is the most electronegative atom there is. Okay, now let's look at hydrogen fluoride. Okay, hydrogen fluoride, you can have a look here. We've got electronegativity in fluorine of 4 as compared to hydrogen of 2.1. So, of course, the fluorine's just going to attract those electrons a whole lot more. So if I, what do I want to do? I want to put in the electric plates. Is that in this one? I can't see it. Okay. And you can just see that the electrons are more towards the electrons, the fluorine, sorry. Okay, let's think water. 3 molecules, I discussed that briefly with you before. Oxygen is a lot more electronegative, 3.5 compared to hydrogen of 2.1, so there's a difference of 1.4 there. So we've got a dipole happening with this. Hydrogen is the positive end, oxygen is the negative end. Let's have a look at CO2. It's a linear molecule. It's non-polar because the two electronegative ends are evenly spread. So it's a symmetrical molecule, and so it's not going to be polar because of those evenly spread oxygens. So even though it's got an electronegativity difference of 1 there. Okay, hydrogen cyanide. You can see nitrogen's a lot more electronegative than hydrogen, so that's polar. Ozone. Have a look at this one. So this is a little bit tricky because the double bond there swaps around and there's a lone pair floating around. So it's a little bit of a trickier molecule. That's O3. It's highly unstable in nature, but it does exist, particularly when lightning hits the atmosphere. Ammonia we've talked about in class, so I might just take off those, that one there, so you can see the shape of the dipole. Okay, electron density, of course, they're going to be a lot more around nitrogen because it's more electronegative. Borane, I should say, BH3. So through VESPA we learned that that was triagonal, and you can see that it's non-polar, and there's only a small electronegative difference there as well. Boron trifluoride, this is most likely going to pop up in your test. It's a classic example, so be aware of that one. Think about the electronegativity difference, so it's 2, so it's pretty well nearly ionic. But have a look at the electron distribution and the symmetry in that, so that's why that's a non-polar molecule. Formaldehyde. So what do we got? CH2O or CHOH or methanol. Okay. What else do we need to know? Methane, we've talked a bit about in class. The tetrahedral shape of methane, and the electrons all clustered towards the carbon in this case because it's the more electronegative, and the hydrogens are evenly spread, so it's a symmetrical molecule. And I should leave the last couple for you to do as well. Oh, you're kidding me. Did all of that for nothing. Pooh.